The next topic in this chapter is ether reactions. Let's first discuss how ethers are created. One way to create an ether is actually to react an alcohol with an electrophilic alcohol to produce an ether. So that's in competition with the elimination reaction. So if I take an alcohol and an acid catalyst, I can create an alkene, or I can actually create an ether. Low temperatures actually favor the Sn2 reaction to form ethers. High temperatures, typically 180 degrees C and above, favor alkene formation. So here is how ethers are made mechanistically. I have an alcohol, I protonate it with an acid, I have another alcohol in solution, which in this case behaves as a nucleophile, attacks my electrophilic carbon because I have water now as a leaving group. My alcohol now forms as a base. It deprotonates that to form the ether. In this case, I'm literally taking ethanol and acid to make diethyl ether. So once I form the ether, can I actually have an OR leaving group? It's actually a very poor leaving group. So just like we did for alcohols, if I protonate that, I make it a good leaving group, but I'm limited to its utility here. Ethers, when they're activated by acids, they're only typically going to undergo Sn1 or Sn2 reactions depending on what the conditions are. So in this case, I've taken an ether, I've thrown in iodo acid here, protonated my oxygen, made it a good leaving group. My iodine comes in, attacks my carbon, and I form an alcohol and an alkyl halide. The reagents like thionyl chloride, phosphorus trichloride, or tosyl chloride cannot be used to activate ethers because they do not have a proton that can be lost to form a stable product. I can't form a stable product with those reactions. Let's take a closer look at the mechanism for ether cleavage to form the alkyl halide and the alcohol using iodide. So if I look at a ether that has a big bulky group on one side of the oxygen, if I add some iodic acid to there, I protonate the oxygen. If that acts as a leaving group, I form a very stable carbocation. So this ether actually favors an Sn1 reaction, where my iodine then comes in and attacks my carbocation. So in this case, I form a small alcohol and a larger alkyl halide. If I look at an unhindered ether, these typically undergo Sn2 ether cleavage, where again I first protonate my oxygen, but this is a very poor leaving group for under Sn1 conditions because I would form a primary carbocation which is not stable. So I actually then undergo Sn2 attack, where iodine is my nucleophile, and it attacks the least sterically hindered carbon. In this case, I still form an alkyl halide and an alcohol. Ethers actually are not very reactive. They tend to react with hydrogen iodide, but very few other molecules. So we actually use them as common solvents. Diethyl ether, tetrahydrofuran, tetrahydropuran, 1,4-dioxane, 1,dimethoxyethane, and this T-butyl methyl ether. These two right here at the end are very common solvents. Ethers are some of the least polar solvents because they're typically symmetrical. They're also very poor Lewis bases, so they're not reactive. Also, ethers can be dried very easily. In other words, you can remove the water through either some drying agent like sodium sulfate, or you could distill them. Ethers also have very low boiling points. We could distill them off. And ethers are cheap, which is a big reason to use ethers also. Let's now talk about some ethers that are reactive. And those are typically epoxides, which are three-membered ring ethers. One reaction that they undergo readily is a ring opening. So let's start talking about ring opening reactions for epoxides. So I have an alkene. If I react that with peroxy acid, I can add oxygen across that double bond to form the epoxide and carboxylic acid. That's one methodology for creating an epoxide. Another methodology is to actually react an alkene and with water to form the hydrochlorine reaction to form the chlorine hydroxyl group, and then react that with sodium hydride to form an internal Sn2 reaction where this oxygen now attacks that chlorine from the opposite side to form the peroxide. This above method is actually more common because it's more versatile. Let's see why epoxides are more reactive than ethers, mainly because of the high ring strain that's higher in energy. If I look at diethyl ether, it is more stable than ethylene oxide, which is the epoxide here. If I undergo a chemical reaction, my ethylene oxide has less energy, less activation energy to go over this activation energy barrier to reduce my products. So it's in fact more reactive. Let's look at some acid catalyzed reactions that epoxides undergo. So here I have a very simple epoxide with 2 carbons on that. If I react that with hydrobromic acid, I can protonate my oxygen, making the oxonium ion. My bromide then can attack one of these carbons, which will be a slightly positive, making it a good electrophile. And due to Sn2 reaction, I can literally form this halogenated alcohol. If I add alcohol to my solution, I can still use a base to protonate and activate my epoxide, but then my alcohol, the lone pair of electrons, can act as a nucleophile, attack one of these partial positive electrophilic carbons, and I'm going to make here, in this case, after extracting that one last proton here, I'm going to make a new ether and an alcohol. If I have an asymmetric epoxide, I have 2 options now for nucleophilic attack. My first step is still to protonate and activate my epoxide, followed by nucleophilic attack of one of my electrophilic carbons. If I look at the product mix, I find out that the more substituted carbon ends up as the ether here, and the least substituted ends up as a minor product. If we look at the mechanism for this reaction, after protonating my oxygen of my epoxide, I'm going to look for the more stable partial positive charge, and that's going to be on the more substituted carbon. So I'm developing a partial carbocation here, which is more stable than my primary partial carbocation. So my ethanol will attack my more stable carbocation, forming my major product here, and then my minor product will be the one for the least stable carbocation. Under neutral conditions or basic conditions, my nucleophile will preferentially attack the least substerically hindered carbon, so I can change reaction. If I take sodium methoxide, which is a source of methoxide nucleophiles, I'm going to attack the least substituted carbon, and in this case my major product is going to be the product where my ether is out here attached to this least sterically hindered carbon. How about other nucleophiles? I could use the acetylide ion, and in this case I'm going to attack the least substituted carbon of this epoxy to form a new alkyne. If I take an amine, which has a lone pair of electrons, I'm going to attack my least substituted carbon to form this intermediate salt, followed by protonation with some acid to form this secondary amine. So it looks like epoxides are very useful synthetic tools for creating new molecules. We are able to do hydration reactions of alkenes using acid catalyzed reagents. However, because we're susceptible to rearrangements, if we go through a carbocation, we get multiple products. Another method for doing a hydration reaction of an alkene is to first create the epoxide and then react it with a source of hydride nucleophiles. In this case, sodium hydride reacts as a nucleophile to open up that three-membered ring. And in this case, I'm going to form the alcohol. I'm going to do a hydration reaction to form the unrearranged product. Rearrangements are always common when I go through carbocations, so we look for alternative methods to eliminate carbocation rearrangements. We saw in an earlier chapter that I can make diols by reacting alkenes with osmium tetraoxide and followed up by a hydrogen peroxide in fairly good yields. Osmium tetraoxide is a fairly toxic material. Another methodology for making diols is to first start with the epoxide, react it with base to open up that ring, so a nucleophile opening up that ring, then finally protonating that with hydrochloric acid to form the transdiol. So in our osmium formation of the diol, I'm going to get the cis-1,2 cyclohexane diol. Using the epoxide, I get the trans-1,2 diols are formed. It's all based on the ring opening mechanism.